Hi everyone, it's Professor Pemberton. In this video we're going to talk about relative rate of change and elasticity of demand. Whenever there's a price increase in a particular commodity, economists use the notation elasticity of demand to study the relationship between price, demand, and revenue. So in this video we're going to find the relative rate of change and the percentage rate of change of a function, and then we're also going to solve application problems from economics and business related to elasticity of demand. So let's start with relative rate of change. Understanding and interpreting rates of change is one of the most fundamental applications in calculus. And to understand how elasticity of demand comes up in economics and calculus, we're going to first discuss relative rate of change. So relative rate of change, it has this definition. The relative rate of change of a function f of x is defined as f prime of x, or the derivative of f of x, divided by f of x. So we're going to look at a couple examples to better understand the relationship between relative rate of change and percentage rate of change. So example 1. Relative and percentage rate of change. Find the relative rate of change of the function f of x equals 3 times e to the 4x power, subtract 2x to the fifth. So our function is f of x. We need to find the derivative of f of x because that's part of the relative rate of change formula. So f prime of x, notice that the first term is a composite function because it's e to a function rather than just e to the x. So you have to use the chain rule. So the derivative of the outside function is, it's an exponential function, its derivative is the same, so 3 times e to the 4x power times d dx of the exponent, which is a function. So derivative of the inside function, derivative of 4x. Subtract the derivative of the second term, use the power function. So 2 is a coefficient, the derivative of x to the fifth is 5x to the fourth, and so you'll get 10 times x to the fourth. And so f prime of x is equal to 3 times e to the 4x power. The derivative of the inside function, 4x, is 4, so you'll have 3 times e to the 4x times 4, subtract 10x to the fourth, and then after simplifying, you'll have 12 times e to the 4x power, subtract 10x to the fourth. After you found the derivative, now you can use the formula to find the relative rate of change of the function f of x. The relative rate of change of f of x is f prime of x divided by f of x. So the derivative goes in the numerator, and the original function is in the denominator. 12e to the 4x power, subtract 10x to the fourth, that's the derivative, and the denominator was the original function, 3e to the 4x, subtract 2x to the fifth. So to get an idea of what the relative rate of change and the percentage rate of change actually means, let's do example 2. Relative and percentage rate of change. Find the relative rate of change of the function f of x equals 10 times x, subtract natural log of 7x plus 5, at x equals 3. Round your answers to 2 decimal places. So if this is the original function f of x, we know that the relative rate of change formula involves the derivative, so let's find the derivative of f of x. F prime of x is equal to the derivative of the first term, derivative of 10x is 10, subtract the derivative of natural log of 7x plus 5. Natural log of 7x plus 5 is a composite function, so we have to take the derivative of the outside function first. The derivative of natural log is 1 divided by the argument, so 1 divided by 7x plus 5, times the derivative of the inside function using the chain rule, so d dx of 7x plus 5. And now simplify, so f prime of x is 10 subtract 1 divided by the argument of the logarithm, 7x plus 5, and then the derivative of 7x plus 5 is 7. And so you'll have 10 subtract the fraction 7 divided by 7x plus 5 in the denominator. So we have the relative rate of change. It's f prime of x divided by f of x. So the derivative goes in the numerator. 10 subtract 7 divided by 7x plus 5. And then the original function goes in the denominator. F of x is 10x subtract natural log of 7x plus 5. So we found the relative rate of change. Now let's find the relative rate of change when x is equal to 3. So now when x is equal to 3, plug in 3 into the derivative in the numerator and plug in 3 into the denominator, which was the original function. So 10 subtract 7 divided by 7 times 3 plus 5, all divided by 10 times 3 for the x, subtract natural log of 7 times 3 plus 5. Now to type this into a graphing calculator, make sure that you put the numerator in parentheses, and you also put the denominator in parentheses, because there are 2 separate terms in the numerator and denominator. So parentheses, 10 subtract, then you have a fraction, so 7 divided by, make sure the denominator goes in parentheses because you want to add the denominator. So 7 times 3 plus 5, close the parenthesis on the denominator, and now close the parenthesis on the numerator of the larger fraction, divided by, the denominator is 10 times 3, subtract natural log of 7 times 3 plus 5, close the parenthesis on the natural log, close the parenthesis on the denominator. So you get 0.363, or if you round to 2 decimal places, you'll get 0.36. Now what this answer means is that this is the relative rate of change when x was equal to 3. Or you can interpret this as a percentage rate of change. You can think of this as a 36% when you change it to a percent. That means that the function is changing 36% whenever x is equal to 3 for the original function, f of x. So we've talked about relative rate of change and percentage rate of change. Now let's talk about the more interesting topic in this section, elasticity of demand. We know that demand functions are decreasing, so when price increases, the quantity demanded goes down. So the more expensive a product is, the less the demand will be. However, we also know that there's a relationship between price, quantity, and revenue. By this formula, revenue was always price times quantity. So when price increases, will the revenue go down because of the decrease in demand or quantity? Or will the revenue increase because the demand did not drop very much? A small decrease in demand may actually increase the revenue when prices are increased. So one of the more useful concepts in economics is the concept of the relationship between the price of a particular commodity and its demand, and this is called elasticity of demand. This elasticity of demand is a measure of how demand reacts whenever the price changes. And it's normalized, which means that at particular prices, quantities do not matter, and everything's treated as a percent. So the formula for elasticity of demand involves two relative rates of change. It involves the relative rate of change of demand and the relative rate of change of price. So we're going to use lowercase p to denote the price per item and lowercase q for the quantity, which we know that quantity can also be represented as the price-demand equation. Elasticity of demand. The elasticity of demand is defined this way. It's capital E. It's the absolute value of this measure, the relative rate of change of the demand divided by the relative rate of change in the price. So elasticity of demand is always positive because you're taking the absolute value of whatever that number is. So with this formula, you would actually have to take the derivative of the demand, you have to take the derivative of the price, and you have to use the formula that we had for relative rate of change. Well, that formula can be simplified. Using the relative rate of change definition, you can find an equivalent formula for elasticity of demand that's more useful. So if you have the price demand function that gives Q in terms of P, in other words, Q is solved for, and P is the independent variable, the elasticity of demand can be found by using this formula, which is more useful. Capital E is the absolute value still, so it's the variable P for price divided by the function Q, which is demand, times dQ dP. Now dQ dP is the derivative of Q, so the derivative of the price demand equation, where P is the variable, which is representing the price. So note that the demand is a decreasing function of price, so the derivative will be negative. So for this reason, that's why the absolute value is around the expression, so that E, the elasticity of demand, will always be a positive number. So what does the elasticity of demand actually tell us? Well, there's three different cases. Whenever you take the absolute value, we'll be taking the absolute value of a number, so that positive number will either be less than 1, greater than 1, or equal to 1. So that's three different cases. If the elasticity of demand is less than 1, then it's what's called inelastic demand. And so what that means is rising prices will increase revenue. If the elasticity of demand is greater than 1, then you have elastic demand, which means rising prices will decrease revenue. So if E equals 1, you have critical points for the revenue function, which means the revenue function will be maximized. We have these three cases where E is less than 1, greater than 1, or equal to 1, but what does it actually mean? The interpretation for elasticity of demand. If the price per item increases by 1%, the demand will decrease by E%. Whatever you find for the elasticity of demand, change that to a percent, and that's how much the demand will change if prices increase by 1%. So let's try example 3. Elasticity of demand. A company sells Q ribbon winders per year at P dollars per ribbon winder. The price demand function for ribbon winders is given by this equation. P equals 300 subtract 0.02 times Q. Find the elasticity of demand when the price is $70 each. Will an increase in the price lead to an increase in the revenue? So the first thing to notice is that this equation does not have Q solved for. You need to have the price demand equation, which has Q on one side of the equation, and it's in terms of P, the price. So we need to take this equation and solve the equation for Q so that Q is on one side of the equation and it's in terms of the price P. So take the equation, subtract 300 on both sides of the equation so that 300 is away from the Q. So P subtract 300 is equal to negative 0.02 times Q, which means that you can now divide by negative 0.2 to get Q by itself. So divide both sides of the equation by negative 0.02. So that way the negative 0.02 will just cancel out on the right side of the equation. And all you'll have left is a Q. So Q is equal to P subtract 300 divided by negative 0.02. Now you can simplify this a little bit further. Notice that you have P divided by the number negative 0.02. So P divided by negative 0.02 is one fraction. And then you have negative 300 divided by negative 0.02 is the other fraction. Becomes positive 300 divided by 0.02. So now simplify. You have 1p. So 1 divided by negative 0.02 becomes negative 50 times p. 300 divided by 0.02 becomes 15,000. So that's what Q is. Q is negative 50 times P plus 15,000. Now let's find out what the elasticity of demand is. The elasticity of demand is this formula. Capital E is the absolute value of the variable P divided by the function Q times the derivative of Q with respect to P. So capital E would be absolute value. P is the variable, so it's just P divided by the price demand equation, which we found was negative 50P plus 15,000. And now we need to find out what is the derivative of Q with respect to P. So let's take the derivative of this equation where P is the variable. So Q prime, the derivative of the left side, is equal to, what's the derivative of negative 50P? P is just a variable. It's not a function, so the derivative is negative 50, and the derivative of 15,000 is 0. So Q prime is negative 50. So you can replace dq dp with negative 50, and so now P times negative 50 is negative 50 times P, all inside absolute value, and the denominator stays the same. And this is simplified as far as possible. You can't simplify any further because there's two terms in the denominator and there's only one term in the numerator. So this is called elasticity of demand. Now let's find out what is the elasticity of demand when the price is $70. So replace all the P, the price, with $70. So you have absolute value, negative 50 times P, that's just $70, divided by negative 50 times P again, so negative 50 times 70, plus 15,000. So whenever you type this into the calculator, you'll have negative 50 times 70 in the numerator, divided by, now there's two terms in the denominator, so make sure you have parentheses around the denominator, negative 50 times 70 plus 15,000. Close parentheses on the denominator. Now you get the answer is negative 0.304, but we need to take the absolute value of this number. So it's going to be 0.304 for the elasticity of demand. Now, since the elasticity of demand is less than 1, we have what's called inelastic demand. What that means is that whenever the price for the ribbon winders are $70, then an increase in price will result in an increase in revenue. So let's talk about the last topic, necessity versus luxury. The demand for products that people have to buy, such as food, tends to be inelastic. So what that means is that whenever the price goes up, people still have to buy about the same amount of food, and the revenue will not go down. The demand for products that people can do without, or they can put off buying until later, such as jewelry, tends to be elastic. So what that means is that if the price goes up, people will just not buy the jewelry right now and the revenue will go down. So example 4, elasticity of demand. A company finds the demand Q in thousands for their kites to be Q equals 400 subtract P squared. So notice that this equation already has Q by itself, where the price, P, is between 0 and 20 at a price of P dollars a kite. So what this means is that this formula only makes sense between 0 and $20 for the price of a kite. Find the elasticity of demand when the price is $5 a kite, and then when the price is $15 per kite. Determine the price that will maximize the revenue for the company. So let's start this problem off by writing out what is the price demand equation. It's Q equals 400 subtract P squared, that's given in the problem. And since Q is by itself already, we know we need to take its derivative. So the derivative of the left side, the derivative of Q is Q prime, and the derivative of the right side, again, P is a variable, not a function. So the derivative of 400 is 0. The derivative of negative P squared is just negative 2P. There is no P prime because P is not a function. So we can use the formula for elasticity of demand. Capital E is the absolute value, the variable P divided by the price demand equation Q times the derivative of the price demand equation with respect to P. So absolute value, P is the variable, Q is the price demand equation, 400 subtract P squared, and we just found out the derivative of Q with respect to P, it's negative 2P. And so simplifying the numerator, you have absolute value, P times negative 2P, that's negative 2P squared, divided by 400 subtract P squared. And again, you cannot simplify this any further because there are two terms in the denominator, there's only one term in the numerator, so you cannot cancel those P squares, you can't. So let's find out what the elasticity of demand would be if the price is $5. The elasticity of demand would be the absolute value, replace all the p with $5, so negative 2 times 5 squared, divided by 400 subtract p squared, well, 400 subtract 5 squared. So if you put this into a graphing calculator, you'll have negative 2 times 5 to the second power, divided by, parentheses around the denominator, 400 subtract 5 squared, and close the parentheses on the denominator. You get negative 0.13 repeating. Now, absolute value of that number would be positive 0.133 if you round to 3 decimal places. Since this number is less than 1, then we have inelastic demand. So that means if the kite is $5, an increase in the price will not change the demand. The demand will also increase, and so will revenue. So let's try $15 now. If the price of the kite is $15, take the elasticity of demand, absolute value, negative 2 times p is now 15, so 15 squared, divided by the denominator is 400 subtract 15 squared. So now if you type this into a calculator, you have negative 2 times 15 to the second power, divided by, parentheses around the denominator, again, 400 subtract 15 squared, close parentheses on the denominator, and you have negative 2.571. So if you take the absolute value, you'll have positive 2.57. Since the elasticity of demand is greater than 1, this is elastic demand. So what that means is that if the price increases, then the demand will go down. So if the price was originally $15, any change in the price to make it go up any more, the demand will go down. And now the last part of the problem said, determine the price that will maximize the revenue for the company. So we know if the kite is $5, any increase from $5, people are still likely to buy it. But if the kite was $15 and any increase from that, people are less likely to buy it. The demand goes down. So there's somewhere between $5 and $15 where the revenue is maximized, where you can increase price and the demand will increase so that the revenue continues to go up. But after that certain price, if the price goes up any further, then the revenue will go down. So there's a maximum somewhere between $5 and $15. Let's find it. So revenue is maximized if you have unitary demand. So take the elasticity of demand formula. Capital E is the absolute value, P divided by Q, times the derivative of Q with respect to P, set it equal to 1. We're going to have to solve this equation. So let's take what we got from the elasticity of demand earlier, absolute value, negative 2 times P squared, divided by 400 subtract P squared, set this equal to 1. Now notice, if you take the absolute value of negative 2 in the numerator, you just get positive 2. So positive 2p squared divided by 400 subtract p squared. You can drop the absolute value now because you've taken the absolute value of negative 2 in the numerator. So you get this equation, 2p squared divided by 400 subtract p squared equals 1. So now how do you solve for p whenever it's in the numerator and denominator? So multiply both sides of the equation by the denominator. So if you do that, you'll have 1 times the denominator, that's 400 subtract p squared, and if you multiply the left side of the equation by the denominator, you'll have the denominator cancel out. So you'll have 2p squared is equal to 400 subtract p squared. Now solve for p. So move all the p squares to the same side, so add p squared to the left side. So 3p squared equals 400. Divide by 3 first before you take the square root. So p squared equals 400 divided by 3. And now take the square root to get p by itself. So p is the square root of 400 divided by 3. So p is the square root of 400 divided by 3. So square root 400 divided by 3 is approximately 11.547. Now p is representing price of the kite, so we have to round the 2 decimal places or the nearest cent. So this is $11.55. If the kite is sold at $11.55, so we have unitary demand, or price elasticity of demand is 1 if the price of a kite is $11.55. What that means for the company is that if the kite is sold at $11.55, their revenue is maximized. So this finishes our discussion on relative rate of change and the elasticity of demand. If you have any questions about any examples in this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you at the next video when we talk about the first derivative test and graphing.